Good morning, everyone. Today, we're excited to present our report on the project titled Enhancing Cloud Storage Security with Homomorphic Encryption and ML-based Access Control. I'm Vipul, and joining me are Abhinav and Medash. Let's begin by understanding the core of this research. This project introduces a secure framework that combines partially homomorphic encryption, specifically the Paillier cryptosystem, with machine learning models like RandomForest and NeuralNetwork. The goal is to ensure that cloud data can be processed even while encrypted, preserving the confidentiality throughout its lifecycle. Meanwhile, machine learning handles dynamic access control by user by analyzing the user behavior, offering strong adaptability and protection against unauthorized access. This solution addresses two key weaknesses of traditional encryption. First, being the lack of security for data in use and static access control systems. Many recent studies focus on enhancing cloud security. Prior research confirms the potential of homomorphic encryption in protecting data without decrypting it. However, the high computational cost and complexity limits its widespread use. By pairing it with optimization techniques like pruning and parallel processing, we can bridge the gap between the theory and practicality. Similarly, the literature supports the use of machine learning to dynamically manage access control, especially when dealing with unpredictable user behavior. Now, I'd like Abhinav to continue the proposed methodology. Thank you.
Our approach is multi-tiered. It combines homomorphic encryption with machine learning for an adaptive class storage system. With Paillier encryption, computations such as addition or scalar multiplication can be performed on encrypted data, keeping it secure even during processing. For access control, they use supervised ML models like RandomForest and SVM, trained on real cloud logs. These logs include user ID, time of access, location, and action type, allowing the system to dynamically classify each access request. The system was built using Python. The PHE library was used for failure in homomorphic encryption. Scikit-learn was used for training machine learning models. They developed a class called Secure Cloud Storage that handles key generation, encryption decryption, and access prediction. The ML models evaluate a user's attribute and decides whether to allow or deny access. The entire encryption classification decision process runs seamlessly. To handle the overhead encryption and machine learning, they implemented several optimizations: parallel processing for simultaneous encryption and decryption, GPU acceleration to speed up model training and inference, model compression to reduce size without losing accuracy, feature selection and tuning to remove irrelevant data and boost performance. These strategies helped us maintain real-time performance without compromising security. From here, Medesh will continue.
Okay. So after seeing the proposed methodology and followed by the system implementation and optimization techniques, we would further see the outcomes of the following. In other words, we would talk about the results and evaluation. So they have evaluated encryption and machine learning performance on both synthetic and the real data sets. So the encryption and the decryption time increases linearly with the data size. For example, here in the graph, we can see that the 1 MB takes just 50 milliseconds, while the 100 MB stretches to 700 milliseconds, showing a direct impact on the latency or as data volume grows. So the later we can see on the machine learning side, neural networks had the highest of the accuracy and the lowest false slash negative rates. So the random forest balance speed and the precision well. The support machine vector also performed reliably about 93%. So this result confirms that our access control system is both smart and secure. Talking about the security and the scalability, the system is extremely effective at distinguishing between the valid and the invalid access attempts. Neural networks had the best results with the minimum false negative positives and negatives. Even under high traffic loads, system latency stayed within acceptable limits. This confirms that the framework is not only secure, but also scalable and deployment ready for the real world cloud environments. So in the conclusion, our system ensures data confidentiality by enabling encrypted computation. It enhances data integrity through adaptive behavior-based access controls. The optimization techniques makes it efficient and scalable. The balance between the security, accuracy, and the performance makes this approach suitable for the further cloud-based applications. So here are the references we have used. Thank you.